Pumpkin! All right, I don't get it. That's silly. All right, here we are. Applications of exponential functions. One of the big ones is interest. Now, here's a cool thing. They know what's up. Don't know who it was. Cool. Check it out. This formula for compounding interest, and this maybe isn't surprising, but I think it's awesome. The exact same math that we use to calculate how money grows. You know what else grows similarly as compounding money? Populations. You can use these exact same formulas, indeed. You can use these exact same formulas to model several different things, which is why they're so cool. We're going to talk about money for a minute, but we can use it to model populations and how they grow. And a cooler one, in my opinion, is you can model how radioactive stuff decays and predict how much is going to be left after some amount of time. It's the same formula. We change the letters, but it's all the same math. Okay, so like 5 to 15 minutes of your time, and then the rest of it's just going to be work. So check it out. Here's our formula from yesterday. We didn't label all these. We're going to real quick. This A of t right here. I mentioned what it was yesterday, but we didn't write it. Does anybody recall?
Yeah.
What is it?
Oh, wait, no, we didn't write it.
Nope, but I said it. I thought you did a hair swip. Okay. That's right. It's your account balance at time what? So that's a maybe. If you plug in a 0, it'd be at time 0. Time t, whatever it is. Now, for this particular one, we'll see in this formula, it's usually years, because that's how money is talked about, but it doesn't have to be. Okay, P. Random question. This P right here is not any of the words that we just discussed. P in context of money. Principal. The principal. Okay, this, when you talk about principal with money, it's like the initial amount that you've invested. Cool, so we'll see that in a variety of situations. In the context of money, any thought on what R might be? Rate. Now, whether it's money or a population, they typically grow. And this part's important. Rate as, if I say I get, I don't know, do you guys know interest rates right now if you buy a house? What would you guess? If you were to buy a house today, $100,000, how much money do you think you'd pay for that house after interest?
500.
Holy cow. I will hook you up with a loan if you need it, if that's what you're expecting. Nowhere near. 7% roughly is the rate, but it compounds. This is a rate as a percentage. Right now, I think the current rate is 7%, which seems super high because pre-COVID it was 1 or 2%. So it's like crazy high right now. However, 20 years ago when people were buying houses and the economy was growing and really strong, it was still 7-ish%. So we were just in a really low value. Okay, this last one, N, that shows up, I guess 2 more. N. Any thoughts?
I just think of a few flips.
Yeah. Video or?
Oh, no, just like everyone look forward.
Okay.
Pretend I'm not here.
Okay. This is how I always stand, just for the record.
Good. All right.
Cool. All right. N. This one. This is alpha, thank you. Number of compounds per year.
Pumpkin. He says it.
What was the thing you shouted last night that nobody replied?
Y-E-L-L, Y-E-L, everybody yelled blue. And he said, go blue.
And nobody did anything.
I know, it's
Love it.
annoying.
Love it. Okay. All right. Cool. Last one, number of compounds. There's only one place in here that I hate the language of English in this. Some of you guys work, right? Anybody here get paid bi-weekly?
Yeah.
So hypothetically, pretend I'm going to hire you individually to do a job for me, and I'm going to tell you I'm going to pay you bi-weekly. How many days do you go between getting paid?
2 weeks.
So you could go 2 weeks, 14 days. But you could also completely justifiably say, oh, it's 3.5. Because bi-weekly could mean twice per week. I hate the language so much. It's not clear. Biannually, is that every 2 years or is that twice per year?
I think I think the bi-weekly is isn't bi like supposed to be different than like dual? Like it would be dual weekly if you got paid twice a week.
I don't know. A bicycle has 2 wheels.
Yeah, but they're not right next to each other.
Biannually means twice per year.
Wait, tell me
Well, but
Anyway, we'll get there. I'm just gonna avoid it. What do you think T represents?
time.
Time. Typically, with money, it's in years. Now, we're going to go a little bit faster through some of this stuff because when you take calculus, hopefully next year, and I hope I teach it, but I can't guarantee it, a lot of this stuff gets so much more natural to think about and talk about when we have a little bit higher level math. Okay, all this is fine. Now, these sorts of rates, they're not super common. More commonly, we have continuously compounding interest. And I'm just going to give us both formulas, and then we'll do maybe a problem together, but we have all this time to do stuff in class. So let's check it out. This one, love it. Very similar formula. What is Euler's number? E. And approximately, anybody recall? Love it. I can't go any further. I don't know the next digits. 2.71828, blah, 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 forever and ever. Okay, there is a situation where we get continuously compounding interest. So, like when you see APR, when you open a bank account, if you have a savings account or a certificate of deposit, which is a CD, which they're pretty good right now, regardless, you're looking at maybe, I don't know, let's hypothetically say 1% per year. Now, there's a few ways you can do that. You can say at the end of 1 year, we'll just give you 1% now, or I can cut 1% into 2 pieces and do it twice per year. So every 6 months, you get 0.5% of what your value is. And we can split it up however many times we want, right? Now, could I split it up so you get 12 per year? So every month, it compounds. Could that happen? Like at the end of each month, I just give you 0.125%. And we just keep adding it up. Could I do it every minute? Like I could do it monthly. Could I do it daily? So instead of 12 compounds per year, there's 365 of them. Could I do it every minute? You could. The numbers get ugly, right? Could you do it every second? Every millisecond, nanosecond? Like you could keep breaking it down. And eventually, it gets such a small thing that we're just going to say, well, there's no time in between it. It just compounds all the time. Or continuously, one might say. Now, this situation is what John Napier and the Bernoulli brothers, who are like the fathers of this stuff. Napier was a big, he was I think French. He's the guy that worked out all the interest stuff for banks. He was a mathematician. The Bernoullis were super mathematician people. They were playing around with all this idea to figure out how banking should work. In that process, what they discovered was unbelievably powerful mathematical objects and ideas that represent stuff all over the place. Continuously compounding interest is one that I care much more about. So we're going to see a similar formula here. A of T. I'm not going to label them again, but it's the account balance. Okay. Compounding monthly is pretty good, or it's okay. Compounding daily is okay. If you get continuously compounding interest, I claim that it's always a pretty good deal. Now, I'm not that Southern. Did you notice I said any words wrong? Continuously compounding interest is a pretty good deal. Pretty good deal. Okay. For real, like this is going to seem so stupid, but if I said, what kind of deal is continuously compounding interest? You say it's what? Not pretty. Pretty good. Okay, there's a reason. And this is a stupid joke that I love. If you get continuously compounding interest, it's a pretty good deal. Check it out. P, E to the RT. Pretty good. Pert. There it is. Pretty good. This, pert. I don't know if I love it or hate it, but we'll make that determination. Now, this situation, if, and let's just look at this formula, and there's some other stuff that we're not going to go through necessarily. If I compounded infinitely many times, just all the time, that's like taking this number of compounds and it gets bigger and bigger and bigger and bigger, right? So maybe it's once per year, or twice, or thrice, or 4 times, or so forth and so on. This is what we get if that number n approaches what? It keeps getting bigger and bigger and bigger, more and more. What's it approaching if we just let it get bigger and bigger and bigger and bigger forever and ever and ever and ever? Infinity. Now, this is being me kind of fast and loose with it. There's some specific stuff that we could do, but I think it's beyond the scope of what we have to do right now. Cool. Continuously compounding interest is what kind of deal? Pretty good. Sweet. And I actually say it's a pretty good deal, which is stupid, and I love it, because there it is. Now, looking at this, just so we can make little tiny extensions, we are looking at applications, right? That's the main topic that we have here. Where there's number, applications of exponentials. We see interest, whether it's compounding or continuously compounding, but it turns out there's all sorts of things that can be applied here. So, just other applications, and then the rest of the time, looks like we'll have 30-ish minutes to work. Other places with PERT. And I'm going to say A equals PE to the RT, because it's going to change a little bit. Okay, if you see P here, that is principal. This is what's telling me that, oh yeah, we're looking at money. There's a principal amount. Beyond that, though, we can get cooler than this. It turns out that in other places when we want to apply this, we can use models that look super similar. And you'll see, like, I'm just going to make one up here. Let's say that we have the amount of something, A, which it could be the account balance, is equal to A sub 0 e to the kt. That looks different, right? I think it does. Is it really any different, though? Like, check it out. A is still A. Instead of P, I just wrote A sub 0, which this is pronounced A naught. This is an initial amount if you wanted it. E is still E. Instead of the rate R, I replaced it with what? K, which is just going to be a growth factor, but it's still going to be a rate because populations grow at some percentage per year or decline. This is the same formula, right? Now, if you want it to look a little bit different, we still can. We could say A sub F equals A sub I e to the kt, which those sub F and sub I, again, same exact formula, right? Exact same formula, I'm just changing the letters around, or different variables. F and I might be nice. What does A sub F seemingly indicate? Final amount. A sub I indicates the initial amount, which is pretty commonly A naught, or your principal if you're talking money. The last one, if I do this instead, F of X is equal to AE to the KX. Does that look, it's a little bit different, but is it really any different other than I just picked different letters? They're all the same thing that apply in different situations. If I were just graphing, I'd probably go with this one. If I'm dealing with radioactive material, and I'll just put these here, radiation, this is what I'm going to deal with. If I'm dealing with population, I'm probably going to choose this model when I'm writing it out. If I'm doing pure maths and I'm graphing and stuff, I'm going to pick this model. And if I'm doing what, am I going to use this one? Money. So, like, they're the same thing that's just represented in a bunch of different applicational settings. Exact same formula. We're going to do one problem together. We can pick it out of the homework. Do you want to do money, population, or radiation? Let's do radiation, because I think that's like the coolest one. Or we can do money if you guys think that's the coolest one. Nothing. They're all the exact same formula. They're just different letters. Let's do a radiation problem. Okay. One example. We are not, gosh, the overlap between physics and chemistry and all this stuff is so cool, and it's what makes math just the most baller thing ever. Do you guys know any radioactive materials? What? Banana. So potassium, right? Potassium is slightly radioactive. Would you be afraid if I put a banana out on the counter, you'd be worried about getting your super radiation cancer? No. Bananas won't give you cancer. Probably. Oh, Chernobyl. What's Chernobyl? It was not a banana explosion, but I like the idea. Have you guys heard of Chernobyl?
Is it that disease?
It's not a disease.
Oh.
Okay.
I think I'm
Okay, two things. First, Chernobyl was a Soviet nuclear power plant like 100 miles outside of Kyiv, Ukraine. So it was the Soviet Union back then. It's also, if you guys have HBO or Max, I think they call it now, there's like a 3 or 4 part miniseries on it that's the best, top 5 television that I've ever watched in my life. It's so good that tells the story of it. Okay, they used nuclear reactions. They made some silly mistakes, which is really lightheartedly saying this. that led to a nuclear reactor exploding. Okay, huge deal. Nobody believed it was happening. They thought it couldn't happen. They're dumb. It happened. Soviets didn't tell people right away. It took Geiger counters and radiation sensors, like in Norway, for the world to be like, wait a second, why are we becoming the X-Men? So just for fun, you don't really get superpowers from radiation, you get cancer. Okay, looking at it. What do they use for nuclear fuel? Because we use nuclear power still. It has such a bad rap. I would advocate that we should use the heck out of it everywhere, and maybe just do smaller things so that if there's a disaster, it doesn't cause huge chaos. Do you guys know of any other nuclear plants other than Chernobyl?
That one in Japan.
Fukushima. You guys were just babies at the time, but there was a big earthquake, and it didn't explode, but it did wind up leaking a bunch of water into the ocean for a little while.
Hot water.
Radioactive water.
Oh.
From that, because you have to cool. Anyway, we won't go into the whole process. Do you know what they use for fuel? So uranium is a good thought. They refine uranium. It's not oil. That's what we use in regular power plants. They use plutonium, which is a synthetic thing. And we're going to make this up. In 1986, just so you know this is when it happened, 1986, we're in Chernobyl. Okay, and I didn't do the research on this, but let's just say that we had a few things. In 1986, Chernobyl, the power plant, the nuclear power plant, it exploded. I don't know the actual number. I'll Google it once you guys are working. Hypothetically, let's say there were 10 pounds of plutonium, and it's an isotope, and we're not in a chemistry class either, but I'm going to write it like this. Plutonium-239. Okay, super radioactive, pretty dangerous, but really good job at heating up water to turn a turbine. They had 10 pounds. You guys all took physical science. Have you talked about radiation? Have you heard the word half-life? Can you tell me what a half-life is? Yeah, 100%. Now, everything has a half-life of some sort. Radiation-wise, what happens is it shoots out protons and electrons and combinations thereof, and you'd have this big chunk of plutonium that, give it enough time, in one half-life, half the plutonium has decayed away. Now, it doesn't mean it just magically disappears. It's really changing into a more stable, likely to be less radioactive material. So you still get a 10-pound rock in front of you, but it's less dangerous because it's half plutonium now. Give it another half-life, and it cuts in half again. So now we're at a quarter of the initial amount. Go another half-life, and it cuts in half again, and it keeps doing that over and over and over. When we're looking at this, we're going to say that plutonium-239, and let's put a comma, 10 pounds of plutonium, I don't need a comma, I don't like grammar, with a half-life of, and this is why radiation stuff gets a bad rap, roughly 24,100 years. Okay, simple question for everybody here. I want to know how much is left, how much plutonium-239 left in, I don't know, let's go quite a few years. How many years do you want to go? Oh, we got to go way more than that. Way more than that. No, we're going forward in time now. So, yeah, like
25th.
we're going to go so much further than that. Let's say after 200,000 years.
Oh.
Now, we can roughly estimate it. Really roughly. I can't work with 24,100 and do easy calculations. But it's pretty close to what number that's easy to work with?
25,000.
Close to 25,000. So let's check it out. This is 200,000 is 8 cycles of 25,000 years. Do you guys cool with that? Cool. So check it out. After the first cycle, how much plutonium is left? So we started with 10 pounds. We're at 5 pounds, right? That's one cycle. Another 25,000 years. A quarter, so we're at 2.5 pounds. Another 25,000 years. 1.25, another 25,000, 0.625, and we're just cutting in half over and over and over and over. I can't do any more than that just with my math ability. Now, it's still going to be dangerous, I think. We're going to find out here in a second. Cool. I want to answer this question. How do we do it? Help me set it up. And before I just say help me set it up, using one of these formulas, I want you guys to start thinking about it. Try to plug in. I'm going to give you like 2 minutes. And then we're going to talk about how to set it up, how I would set it up. Might not be the same as yours, but that's okay. As we look at these, my guess is you're using this one. Okay, there is, maybe intentionally, one little piece that we're going to think about and say that, man, maybe we can't quite use this yet. But that's okay, because all these things that deal with interest can be applied to these settings, right? Man, if only we had another way to talk about interest. Well, do we have any other formulas that we used? Ooh, hey, we have pretty good, right? But do we have one that's less good? I think so. As we look at it, we can try this one. And let's try it. Let's see if we can set it up, and we'll see where we fail. But let's just dig in with it first. What are you going to plug in? I'm going to use that formula. I like it. A sub f equals a sub I times e to the kt. Like, that's probably the natural choice. Okay, couple approaches here. Do you know a sub f? Do we know how much we're going to be left with? No, not yet. Okay, do you know a sub I? It's 10, right? So I'm just going to plug in what we know here. I know that this would be 10. E is just a number e. I know that time t is 200,000 years. There's an issue with where we're at mathematically, though. At least a little one. What's the issue? We don't know k, and we also don't know a sub f. We have one equation on the board and 2 unknowns. Is this going to work yet? So that's all right. We're just going to make a comment here. Love this approach. Everything we've done is correct. Unfortunately, today, we can't find k. You'll be able to by like next Tuesday, but we can't do it yet. That's all right, because we can make sense of what's happening with this with other exponential models. This is the best model that we could ever come up with. We'll use this model, and we'll revisit this problem in a couple days, but let's check it out. We can make sense of this further. Every so long it cuts in half, right? How long does it take for it to cut in half? So 25 is what we used as we said it, but 24,100, right? So let's just try another approach to see if maybe without all this fancy stuff that we'll use eventually, we will, maybe we have simpler techniques that'll get the same answer, at least close. Remind me, what's the form of regular just exponential function? You might have to check your notes. A to the x, that's the most basic one, right? Now, could we make it so it says something like this? Is this still an exponential? A times b to the x. Is that still exponential? For sure. And gosh, it kind of looks like this, doesn't it? Except instead of e, we're using this number b. Everybody see that there's a connection between this and this. Okay. E is this lovely number, 2.718, that you probably have no understanding of why it shows up here and its significance. That's okay. This is still our initial amount, I think. Let's just see what shakes out here. If we use this, what's our initial amount? 10. And then this one, we don't have a rate, but we can think it out. Gosh, when we were trying to calculate out just in our heads what it was going to be, I multiplied or I divided over and over by what number? I divided by 2 because we're talking about a half-life, right? Is that like multiplying by something? Is dividing by 2 the same as multiplying by something? Same as multiplying by what? So let's just think about what would happen if we do it like this. This exponent right now, if I let this be a 1, and I'm going to use yellow, don't write it, I'll commit back to green. If I put a 1 here, that's like I've run through how many half-lives? 1, because that would be 5. And that's the number we came up with, right? If I put a 2 here, that's like I've run through how many half-lives? 2. Now, unfortunately, the number isn't actually 24. It's not actually 25,000. It's this ugly thing. How would we figure out exactly how many half-lives we need to get this total year? You divide. So instead of just using a single variable, let's knock that out. I'm going to do some scratch work. And I'll go back to green, and then we'll plug it in here in a second. Scratch. Huggins, what you missed, I didn't write down. All this is awesome. This is how I'd like to solve the problem.
What's the 10?
The initial amount. Unfortunately,
Okay.
there's two unknowns in this equation, and until Tuesday, I think, we won't have the skills to do it.
Okay.
So this is a good first step. We're trying to find another way to do it.
What's T?
Time.
But why is... Oh, okay, my bad.
So I'm just using a different looking model. It's still exponential, but it's not this PERT thing. All right, so scratch work with this. Gosh, you said division, Barsega? What do you want to divide to see how many half-lives we're taking? $200,000 divided by 24,100. Okay, this is just our time, right? Now, it's going to be 200,000 in this situation. Any issues if, since we're using x, I can just say, oh, it's x divided by 24,100. And now all of a sudden, any number of years x that we want, we can figure out how much is left. Conceptually, yay or nay? If this were a nicer number, if we use 25,000, 100,000 years would be how many half-lives? And if you did 100,000 for x divided by 20, you would get 4. This is just that number of half-lives. Okay. Is this thing reasonable as a function? Do we know how much time x in this situation? Because why not? Do we know how much time we're trying to use? This model is going to work. It's going to cut in half however many times we need it to. So here's our model, and then let's go ahead and actually just evaluate it. And this becomes a calculator problem. You can tell me if you hate it, but I don't know that I have a better way. I'm trying to find the amount left after how much time? If I make the leap and I say it's y of 200,000 instead of f of this, are we still cool to plug this in? So here's my challenge. On your calculator, go ahead and evaluate this function. I want to see what we get.
What, when it's a sub I,
Yep.
why does it just turn to 10?
What's the initial amount of uranium that we had?
Oh, it's a initial.
Yeah.
Okay.
Yep. A sub I, not the imaginary number.
Yeah.
Yep. Good question. That can be misleading.
I don't know. I just and y equals ab to the x is what?
It's just an exponential function because what winds up happening is on this one, we can't solve to get what k is.
Why? Because we don't know.
Because there's two unknowns and there's only one equation. Now, there's some clever tricks around it, but we just don't, we'll see them on Tuesday. So we're saying, oh, this is exponential though.
Why won't we see him on Monday?
We will see it on Monday. We just don't have the skills to solve this yet.
Oh, okay.
But we're building up because I know where we're going. So we say, oh, this exponential is too hard for us, but maybe this one will work, where half-lives are just cutting in half over and over. What do you guys get? Okay, I'm going to type it in real quick because I just got two different answers and a lot of quietness. How did you guys type it in? Did you go to y equals?
2.5 e to the -5.
Okay, so I'm just going to type it in. I'm on y equals on my calculator. I'm typing in exactly this. 10 times 0.5 is I'm going to type to the power of x over 24,100. And I'm doing it here. You could do it just line by line and type it in. But if I want to know the time at another, or the amount left after another amount of time, then we should probably be able to do that quickly. I have this typed in then, and y equals. How do I evaluate y of something? Vars, y vars, function, y1. And we're trying to figure out 200,000 years, right?
You have to go back.
Okay, somebody got 0.0318. 0.0138. Just kidding, 318. Verify for me you get this number.
What the? Wait, how many zeros do I have? 1, 2, 3. I have only 3. No, I missed the zeros. Okay. What?
That's 200,000. But I'm going to click here though. That should be 10. Nope. That's your shape. Now, check it out. People don't always see this. Don't just type 1 because it's going to replace it. If I want to insert something in front of this, I'm highlighted. Second, insert. Here's your 10.
Are you serious? You have to do that?
You can. Or you can retype the whole thing. Okay. I get this much. Now, doesn't happen all the time in here. This is what unit? The initial amount was in pounds. What's the final amount in? So 0. A quarter pound, not even a quarter, I'm sorry. 0.0318. So that's 0.3 of a pound. That's almost nothing left after 200,000 years. If I had a quarter pound roughly of plutonium-239 in here and I just plopped it on the, like right there, would you guys be cool with that? No, not even a little bit. Not even a little bit. You would have radiation burns and sickness by the time you went home today. Wouldn't do it. Cool. Now, looking at it, has it been 200,000 years since the Chernobyl accident? No. So if you have this already typed in your calculator, Chernobyl was in 1986. We've been 28 years. Do me a favor real quick. If we started with 10 pounds, which is a made-up number, we're going to figure out how much it really was. How much is left today if we started with 10 pounds? So we got 9.99 pounds. It's still all there, still as dangerous. We can look at that, actually. It's called the elephant's foot, one of the scariest things on our planet. Cool, I will. Okay, looking at it. That went longer than I was expecting, but that's okay. I want you guys to work as many of these as you can today. I want 15 minutes of work outside of the classroom today, over the weekend. 15 minutes, that's all it takes. Leave it for Sunday because there's busy days, or academic lab tomorrow if you want to come. We can check it out there. But I'm going to give you a lot of problems to do this real quick. And I lied. I'm going to pick and choose. Homework, what is this, 3.1? Okay, you will find this on page 208. And let's see, I'm going to kick off about 80% of the problems that I've given historically. So let's see here. I want you to do 13 through 16. They're going to be sporadic, just so you know. 13 through 16. 51 through 54.
That's it.
Yeah. Ooh.
So
Ooh. 70. A and B. There gotta be one more good one in here. Nope, that's it. That's all I got. Okay, those. Now, a couple things that just so you guys can see. Calc Chat. How many of you guys use Calc Chat regularly? You use it? Good. You should. Calc Chat's the online solutions manual where you have detailed work for all the odd problems that we've talked about. There's a link to it in the classroom. Alternatively, you cannot take it. Here is the paper version of the solutions manual. You can look at it anytime you want. Pretty sure this has all of them, evens and odds. I'm going to leave it on this front counter. Do me a favor. Don't just cheat. You just copying your homework grades worth like nothing. If you want to take a picture of stuff, you can. It doesn't bother me. But I need you to try the problems first. This is used as a verification, not as an answer. Cool, cool? All right. You're welcome to grab it, take a picture, whatever, whenever. It's here for you. Sweet. So I'll give you guys, sorry about that, 12 minutes. How much time outside of the classroom? 15. God, I didn't give you any graphs.
It's okay.
Can I do my quiz, please?
Yes.